example 512. The goal here is to find the magnetic vector potential for an infinite solenoid. And that solenoid is built with a wire carrying current I and N turns per unit length. And it has a radius R. Okay, so let's go ahead and try to draw that. Here's our solenoid. It extends to infinity. I have a current traveling through a wire. Those are tight turns. So the wire is just in the theta hat, or the phi hat direction. It's carrying a current I. Right. Okay, so I don't know what the magnetic vector potential is. We have one expression for calculating the magnetic vector potential, which says that if I go ahead and integrate the current kind of like our Biot-Savart law, right? Integrate the current, then I can calculate the magnetic vector potential. But we cannot use this because our current density goes all the way to infinity. Just like we can't use our scalar electric potential when we have charges at infinity. So we can't do that. And we're going to employ a little trick. We are first going to say, all right, let's imagine that we can add up all of our vector potential along the path. Okay, I have some field A. I can do a path, a closed loop path interval. We have fundamental theorem for curls that allows us to then write that instead of being a path integral, but as an area integral. Of the cross, or the curl of that vector field over that whole surface that is bounded by that path dl. But we know that this curl of A is just B. So that's B, all of the magnetic field going through a surface, and that therefore is equal to the flux. All right, that's all of the field going through a surface. So this looks a lot like your B dot dl is equal to mu naught I enclosed. But so now all we need to do is we need to figure out what the magnetic field is going through a surface that is defined by a path, and then we can calculate our magnetic vector potential. Okay, so luckily we have done part of this problem before. We know that for an infinite solenoid, the magnetic field is mu naught Ni in the z hat, where we're calling this the z hat direction. That's inside, and then outside of our solenoid, our magnetic field is 0. All right, so let's figure out what the magnetic vector potential is inside. I'm going to go ahead and say that A dot dl is equal to B dot dA. All right, and the first thing I need to do is I need to define a path and a surface enclosed by that path for me to have to evaluate these dot products on. Okay, so I'm going to draw my solenoid again here, and I know that the magnetic field inside is all pointing up, and I need to pick a path that has some sort of magnetic flux that goes through it. Okay, so the strategy here is going to be, all right, well, we can go ahead and choose a circular path and have it aligned or sort of concentric with the cross-section of our solenoid. Okay. So I can have some loop R, I can go around that path, and then the surface that I'm choosing is going to be just the simplest surface for that path, which is the flat plane that connects those, that's enclosed by that. Okay. So that's the smallest surface. Okay, well, I'll do the left side in red. The inside, I'm going to get that just like we do with our Ampere's law. I get A times 2 pi R. And the right side is B dot dA. That is mu naught Ni integral of dA, which is mu naught Ni pi R squared. And therefore, our magnetic vector potential is mu naught Ni over 2 times R. All right, and then I have to go ahead and afterwards put that direction. That direction comes from taking this dot product in the first place. So my magnetic vector potential points in phi hat. Does that make sense? Yeah. It at least isn't obviously wrong. My magnetic field points in the z hat direction, and I know that the magnetic field and the magnetic vector potential are perpendicular to each other, so it is at least possible that is correct. What about on the outside? So this was inside. On the outside, I still have these same paths. A dot dl is equal to B dot dA. All right, let's draw our paths again. Draw this. Okay, I still have A 2 pi R, but now my magnetic field doesn't pierce through the entire piece of my loop, right? It just pierces through this. Okay, so that integral is mu naught Ni dA still, but now this is not, so this is, this integral is, I'll just go ahead and write the whole thing, mu naught Ni, I want to integrate from 0 to R, 0 to 2 pi of R dr d phi. That gives me mu naught Ni pi capital R squared. All right, see how that's different than this one. And therefore, our magnetic vector potential on the outside is equal to mu naught Ni over 2 R squared over R in the phi hat direction. Good, that also decays as opposed to growing as I make my loop bigger.